Hello, in this video we are going to talk about 4 examples that involve the row space and column space, and even talking about the null space a little bit. 2 of these examples will come from the book, 2 of them I made up myself, so let's just jump right into it. So on the screen you'll see that I have put a matrix, and I asked for the basis for the row space and for the column space of that matrix. So this is kind of 2 different problems, but they will involve the same steps at least initially. So in order to talk about a basis for the row space, we would like to put this in a row echelon form, because as we saw in the first video, in the definitions video, that that doing Gaussian elimination does not change the row space. So let's just go ahead and do that. So I'm just going to kind of draw arrows between the matrices as we go. Hopefully I don't take up too much space because it's a little hard to write on this tablet. So first things first, I want to select a pivot for the first column. Obviously this one here is enticing. So we'll go ahead and move that one to the first row, and then we'll use the other stuff in that row, these numbers here, to modify the rest of the numbers in the matrix. So let's just move that second row to the first row. Come on. Just having a little bit of trouble writing there. Sorry. We'll use that one to then change all the rest of the first entries to zeros. I guess I'm taking up a little bit more space than the original matrix. Obviously, what we're going to do to get rid of this 2, we're going to subtract 2 times this row from the old first row. We'll put that in the second row here. So 2 minus 2 times 1 gives us 0. Negative 4 minus 2 times negative 2 actually gives us another 0. Negative 1 minus 2 times negative 1, well, actually, we just end up multiplying, we just end up adding 2 to, well, adding 2 to the negative 1, so that becomes a 1. And as we can kind of see here, since these are all negative 1s, whatever we do with this negative 1, we'll do the same thing with these other negative 1s. So we added 2 to that, we'll also add 2 to the negative 5 and the negative 1. So negative 5 plus 2 is negative 3, and negative 1 plus 2 is 1. Do the same thing with the other 2 rows, or the other 3 rows. So this 3, we're going to take 3 minus 3 times 1. That gives 0. Negative 6 minus 3 times 2, negative 2, is also 0. And then, again, we're going to be subtracting 3 times negative 1, so that means we're going to be adding 3 to everything in the rest of the row. So negative 5 plus 3 gives us a negative 2. 3 plus 3 gives us a 6. Negative 5 plus 3 is again a negative 2. Now we're going to add 2 times this row to this one, so that'll give us a 0 there. 4 plus 2 times negative 2 is again a 0. And then we're going to end up subtracting 2 this time from all those. So 1 minus 2 gives us a negative 1. 5 minus 2 gives us a 3. And then 1 minus 2 gives us a negative 1. And then finally, our last row is actually the easiest one. We're just going to add our pivot row to that row. So again, we get a 0, but then we also get another 0 here. So that's kind of nice, but obviously this has been designed to work out a little nicer than some examples. Then we add negative 1s to each of these, so we again get a 2, negative 6, and a 2. Now this is not in row echelon yet, so we're going to select another pivot. Well, actually in the second column, we don't have anything that would work as a pivot. We had to skip that one. We'll just leave all those zeros there. And now this 1 is a good choice for our next pivot. It's even in the best spot for it. So we'll go ahead and pivot off of that 1 and get another matrix. That first row is going to stay the same. Our second row is in fact going to stay the same as well. We're still going to have zeros here. And our goal is to make zeros here. We're going to use that 1. Again, we're going to try to cancel out the -2, the -1, and the 2. So we'll add 2 times this row to our third row. But then 6 plus 2 times -3 actually gives us another 0. Lots of zeros in this one. That's a very nice example. Then -2 plus 2 times 1 is another 0. And hopefully it's not too hard to see that the same thing is going to happen for the rest of it. So if we add this second row to our fourth row, everything just cancels out. We're going to get all zeros here as well. And finally, we need to subtract 2 times our second row from our fifth row. And again, everything is going to cancel out. So this is a rare example of where doing Gaussian elimination actually gives us a row echelon matrix in only 2 steps, even if we start with a 5 by 5 matrix. So this is definitely in row echelon form already. And technically, at this point, we could stop and use what we know from this matrix to actually tell us something about the row space and even the column space. But in some situations, it's actually better to go one more step and actually get it into reduced row echelon form. So we'll go ahead and do that. We'll go ahead and make a reduced row echelon form, so RREF, where we change. Remember, reduced row echelon form means that anything that has a leading 1 cannot have anything non-zero in that same column. So this -1 is actually our big problem. So actually, let's go ahead and circle that. This is our problem spot for putting into reduced row echelon form. Most of the stuff is going to stay the same. In fact, we're not even going to modify the 1 or -2 in the first spots in here. We want the -1 to become 0. A lot of these zeros are still zeros. I need to stop putting my parentheses before I actually put in the numbers. Our second row is not actually going to change. We're still going to have 0, 0, 1, -3, 1. Our 3 rows of all zeros are still all zeros. And now, what we had to do to change that -1 to a 0 was we added the second row to the first row. That's going to modify the other -1s in that row as well. So -1 plus this -3 will give us a -4. And then -1 plus this one will give us another 0. So this is the RREF for the matrix A. And from that, we can actually get a lot of information about the row space and the column space. In fact, for the row space, we already can tell a basis for it. So the row space basis. Now, because of these 3 rows of all zeros at the bottom, we don't actually use those. So those do not contribute to a basis. We can't have 0 in a basis, the 0 vector in a basis. So we're going to take these first 2 rows, so 1, -2, 0, -4, 0, as our first basis vector. And then 0, 0, 1, -3, 1 as our second basis vector. This is a basis for the row space of U and for A because they share a row space. And so you can actually say that the rank of A is 2. It's two-dimensional. It has two basis vectors. These are actually linear independent vectors once we've done all the row operations and gotten down to REF or RREF. Now, as I did mention before, we can use just the regular REF. This is not the only possible basis for our row space. We could have used the first two rows of our REF matrix. So 1, -2, -1, 1, -1, -1, and then 0, 0, 1, -3, 1. It's a little bit more awkward to write on this pad, so I'm sorry that it looks a little sloppy. Hopefully that will improve as well as we go as well. But we'll make do as we go. But this is also another basis for the row space. They're the same subspace, exactly the same subspace, just a different basis for it. In fact, we could actually look at a third possible basis for it. If we really do want to be talking about the rows of A, we could go back and look at what rows of A actually survived the Gaussian elimination. So remember, we did do a row swap at the very beginning. That actually can have an effect on what rows do we actually use for our basis. So this first row of U, the one that's our first basis vector for our row space, it was originally the second row of A. That means that if we want to make a basis for the row space out of actual row vectors of A, we would go ahead and use that second row of A. So if we can write that down. So 1, -2, -1, -1, -1. And then we look and see that the second row of U, that was actually originally the first row of A. So we then go ahead and use that first row of A. So we could have a second basis vector of 2, -4, -1, -5, -1. And this is another basis for the row space. These, again, same row space, but just another possible basis, another possible answer for this question. Of course, the order doesn't really matter. We could have put these in the opposite order. We just had to know which rows actually did survive the Gaussian elimination process. Probably I should have said bases, pluralize that, bases. Okay. Now, those are bases for the row space. What about bases for the column space? And that's a little bit of a tricky question. Doing Gaussian elimination does change the column space. But the process of Gaussian elimination does actually give us information about the column space. So if we look at, let's label the rows and columns of U and A. Or not the rows, just the columns. So let's say this is A1, A2, A3, A4, A5. Those are those columns. And then for U, we have U1, U2, U3, U4, U5. And let's think about what relationships there are between the columns of U. So if we look at U3 and U5, those are actually exactly the same column. We could actually just say that U5 equals U3. We kind of want to reference the earlier vectors if we can. U2 is actually not too complicated either. It's just u1, but times -2. If we multiply u1, the column u1, by -2, we actually just get the same column as u2. So we're going to put u2 is just -2 times u1. u4 is probably the most complicated one because it's not just made up of previous vectors. Well, it's made up of previous vectors, but not made up of just one previous vector. What we can see here is that this -3 we could get by multiplying u3 by -3, and the -4 we could get from u1 by multiplying by -4. And if we add those two together, we would get u4. So that's what we're going to write here. u4 is -4 times u1, then -3 times u3. In other words, the columns are all just linear combinations of two columns, u1 and u3. Obviously, u1 and u3 are linear combinations of themselves, but then each of the other three columns are also linear combinations of those two column vectors as well. And actually, it will turn out that the dimension of the column space is 2. That is spanned by u1 and u3, at least for the matrix U. Not for the matrix A. We'll come back to that in just a second. Actually, let's give myself a little bit more room. I'm going to erase this. Or it's not going to erase. Okay. Sorry about that. Here we go. All right. Let's look at how the columns of A are similar to the columns of U. They're not the same ones, but they are similar. In fact, if we look at A2, it is a multiple of A1. Everything in the column column 2 is just -2 times everything in column 1. It's in fact the same relationship that we had in the matrix U. We have that A2 is -2 times A1. In fact, A5 and A3 are exactly the same. We do have that A5 equals A3. They are the same column. The one that's a little harder to see, of course, is that A4 is not immediately just a multiple of the other ones, but if we compare to U and we think about it, A4 is actually -4 times A1 minus 3 times A3. So we can look at this and see that -4 times 2 and then -3 times -1, that will be -8 plus 3 and gives us the -5 that we expect here. And that will hold for everything else in A4. It turns out that even though we did change the column space, the relationships between the columns do not change. They are the same ones as the original matrix. And so if we think about a basis for U, we formed a basis from U1 and U3. It turns out that using A1 and A3 will give us a basis for the column space of A. So let's write that over here. Column space. We can just take A1 and A3. I'm just going to go and write those out. So 2, 1, 3, -2, 1, -1 is A1. And then -1, -1, -5, 1, 3 is a basis for the column space of A. So row operations does change the column space, but because we can actually use the same relationships as we find in the reduced row echelon form to make the column space of A, we can actually use the information from Gaussian elimination to do that. So essentially it boils down to what are the leading ones that we get in our reduced row echelon form, or even the RRE, just the regular row echelon form. We had a leading one in column 1 and a leading one in column 3. That means that we keep columns 1 and 3 as a basis for the column space, or at least a possible basis for the column space. Next up is a problem from the book. We're going to work out problem 3 from the exercises in this section. So they give us a matrix A. This is a 3 by 6 matrix, and they have multiple parts to this. The first thing they want us to do is compute the reduced row echelon form matrix U from this matrix A. So very similar to what we just did, but just with a different example. So again, I'm just going to draw arrows to the new ones. I'm going to use this first one. So this one is a good thing to pivot off of. So I'm going to keep this first row, but I'm going to change everything else in that first column to a 0. That first row stays the same. And then what do we get in the rest of it? Well, we're just going to subtract 2 times that first row from the second row. That gives us a 0 here. It also gives us a 0 here. And then the other ones, I'm just going to go through these a little quicker than I did the last one. We'll get a 1, -1, 2, and just +1. Let's write a negative. In our third row, we're going to take 3 times the first row and subtract it from the third row. That's again going to give us a 0 here, as we want, and then give us a 0 here as well. In the other spots, we're going to have a 1, -1, 2, and this one's a little different, so we actually get a -3. Now again, we don't have the row echelon form yet. We're going to want to change this one, or keep that one as our next pivot, and change that one to a 0. So our next step, again, we're going to have 1, 0, 0 for first column. We still have 2, 0, 0 for our second column. We're going to have 2, 1, 0 for that column. That's what we want. The stuff in the first and second row are going to stay the same for now. And then we're going to change what we have here. We're going to subtract the second row from the third row. And that's going to change, well, it's going to make this a 0 here. We're also going to get a 0 here and here. Hopefully that's kind of easy to see why that happens. But then for this last slot, we're subtracting 1 from -3, so we get a -4. Well, not quite row echelon form yet. We didn't look out quite as much in the last one, but we're not too far off. The main thing to note here is that if this was a 1, then we would be in row echelon form. So I'm going to change that to a 1. Basically, I'm just allowed to divide that third row by -4 to change it to whatever I want it to. Just change it to a 1. If there's only one thing in a row, I can change it to whatever I want through use of row operations, aside from 0, of course. So I'm going to change that to a 1. And I'm also going to then use that to actually go back and put it into the reduced row echelon form that we want. So remember, in reduced row echelon form, what do we need to have? We need to make sure that everything that is in the same column as a leading 1, so that like that 2, this 1, and this 4, those need to all change to zeros. We cannot have another non-zero number in the same column as a leading 1. So we ultimately get the matrix U, the reduced row echelon form matrix U. Well, it's not going to change the 1 or 2 here. We're still going to have zeros here. We're still going to have a 1 there. In fact, this -1 and this 2 don't change. Like I said, we're going to change that to a 1. And we're going to change those to zeros. And so what do we get in the other two spots? Well, keep in mind, what did we do? Well, using that 1, we actually just went ahead and canceled out those pretty easily. We can actually cancel those out without changing anything in the rest of the matrix, because we can't change anything other than the last column with this third row. But when we go back and change this to a 0 by using this 1, this -1 and this 2 actually change what we have in these two spots. So this 3 actually turns into a 5, and this 2 changes that 1 into a -3. So we basically just subtracted 2 times the second row from the first row. And this is our well, at least the first part of part A. So we computed the reduced row echelon form of the matrix A. Now, what are the free variables of, or which column vectors of U correspond to the free variables if we're treating this as a linear system? Well, they're all the ones that don't have leading ones. So our second row, our second column, our third column, fourth column, and our fifth column. These are all correspond to free variables. Write each of these vectors as a linear combination of the column vectors corresponding to the lead variables. So we're going to do the same thing that we did in problem 1, in our first problem. We're going to think about what is the relationship between the ones that actually do have leading ones and the ones that don't have leading ones. So if we were to label these, so say U1, U2, U3, U4, U5, and U6, what relationships do we have? Well, U6 is actually not related to any of the other columns, but we do have things like U2 is just 2 times U1. So we can go ahead and write that out. U2 equals 2 times U1. U4, well, we can make that up by taking 5 times U1 and then subtracting U3. And then finally, for U5, U5 is just -3 times U1 plus 2 times U3. So now we've expressed every single vector in terms of the vectors U1, U3, and U6. We didn't have to use U6 because it's just off by itself. It's the very last row. And nothing else has a non-zero number in that third row. Now, as we saw with problem 1, these same relationships actually hold in the matrix A. If we label all the columns of A, and okay, not lining these up pretty well because I'm writing a little bit bigger than I have the magnification of the text at. But if we label those A1 through A6, then we still have that A2 is just 2 times A1. If you look at the second column of our matrix A, everything is just double what we have in the first column of matrix A. And then A4, so again, this is a little bit harder to see, but since we've already looked at our matrix U, we actually can identify that this is just going to be 5 times A1 minus A3. And again, A5 is going to be -3 times A1 plus 2 times A3. these same relationships still hold, and we could go back and actually verify that every single one of them still actually do work. So our basis for our column space just consists of A1, A3, and A6. So let's actually just go ahead and write those out. So A1 is 1, 2, 3. A3 is 2, 5, 7. And A6 is 4, 9, 9. Our column space is three-dimensional.